And then, of course, mercury. What's the symbol? Mercury.
HG.
Not M.
HG.
HG. Mercury. And let's see. Okay, let me just pass these around so you can take a look at those. And that's the elements, and to know there's about 100 of them. And the other thing to know from that, where did I put my pencil down? Somebody's going to have to be the pencil marker watching because I lay them down. Oh, here it is. Okay, our next one here is compounds, and with compounds we have 2 or more elements combine in a definite ratio and usually hard to separate. Okay, compounds, another type of pure substance. Water is a compound. Okay, pure water is the same no matter we get it here, you get it in Antarctica by melting ice. If there's nothing dissolved up in the ice water before it started. So compounds, 2 or more elements combined in a definite ratio. Okay, we write it as formulas. Okay, water, H2O. And let's just look at some of the tricks. There's about 3 tricks in formula writing. We talk about a symbol for an element. We talk about a formula for a compound. And how are you going to be able to spot compounds? You're going to see 2 or more different elements slammed together with no spacing. So we have H2O. Trick number 1. We have subscripts here to tell us how many. Chemists are too lazy to write ones. If there's not a subscript, it's understood to be a 1. So think of, over the years, how many of these I have saved by not putting ones on all the subscripts. But what do we understand about this is, if you have a water, you have 2 watts. What's that H? Hydrogens. We got 2 hydrogens and we got 1 watt. Oxygen. 2 to 1 ratio. Whereas, something that looks kind of similar, does anybody know what that stuff is? Hydrogen peroxide. Good. Hydrogen peroxide. Totally different. You do not want to drink that stuff. I mean, it may look like water, but you don't want to drink it. So, what is the difference? It's 2 to 2 instead of 2 to 1, and that makes the properties totally different. And again, reading in the Chronicle, the impeccable medical source. When hydrogen peroxide is not real stable, and it breaks down and gives you water and gives you oxygen. You know, when you put it on a cut and there's blood, okay, something in your blood helps the breakdown of that, and it bubbles if it hits blood because it's going to turn into water and oxygen. And evidently, that high oxygen content will help kill bacteria that are in the area. Okay, so a few years ago, people got the idea, health food store people, that why don't you just drink a little hydrogen peroxide? Okay, it'll break down and you'll be oxygenated, because to think clearly, you need oxygen. Well, really dumb idea. First of all, it goes in your stomach, so you've got gas in your stomach if it's breaking down, not in your lungs, so all you need to do there is burp. But if you take in too much, it can kill you. So this story from the newspaper several years ago, a woman in Florida decides her 2 little kids aren't doing well enough in elementary school. You can see what's coming. So she makes both of them drink each morning a little bit of hydrogen peroxide. One died. The other one recovered, but she killed one of them with it. So sometimes a little knowledge is dangerous. You know, yeah, it breaks down, gives you oxygen, but you don't want to be drinking it. Use it on your wounds, not in your mouth. So, compound, compound, different ratio. So this is trick 1. The ones aren't shown. Now, trick 2. Parentheses. Okay, if you have parentheses, what this means, the subscript behind your parentheses means you have 2 of those NO3 units. Again, it has to do with being lazy. Instead of writing like that twice, you're just putting parentheses around it, because NO3 is something that acts as a unit, so you don't want to write N2O6. but you want to write it as the unit. And we'll talk more in a later chapter about those units. But let's take a look at that. Let me ask you a whole bunch of questions here. How many different elements do you see in that? Three in that compound. Okay, we've got a Cu. What is it?
Copper.
Copper. How many? One. N is nitrogen. How many do I have?
One.
Wait.
Two.
2. Raise your bid.
Oh.
Okay, that was an aha moment over there. Okay, parentheses. That means 2 times everything in there. So we have 2 nitrogens. Okay, you're on. How many oxygens do I have?
6.
Excellent, excellent, excellent. Okay, so know what the parentheses mean. That was trick 2. Now, here's trick 3, and it's much rarer than the other tricks. Sometimes you see a dot. And it's not like in math where it could mean multiplication. And what almost always follows that dot is water. Okay, what this means, and this compound is different in properties than this compound without the dot and without the 5 waters. What's happened here? This is referred to as water of hydration, and when this copper sulfate has formed, it's trapped water in the crystals of it in a definite ratio. So it's actually a part of the formula. So it means 5 waters. So that's essentially very similar to the parentheses trick. Okay, so let's go through this substance. And remember, this is trick 3. Okay, let's just run through and everybody can answer. I got Cu and it is copper. How many? 1. S is sulfur. And how many? 1. Okay, now, O is what? Oxygen. What's the total amount of oxygen I have in this compound?
9.
Okay, I'm hearing 6, I'm hearing 9. Okay, here's 4. And I've got 5 more. 9. The highest bidder one. Okay, so there's 9 oxygens. How many hydrogens do we have? 10. Okay, so compounds. 2 or more elements in a definite ratio, 2 to 1, 2 to 2, whatever. The subscripts tell us. So the first thing you should be able to do is, first of all, if I wrote a list, I have O and H, element, compound, compound, element. Just recognition. And then if we have a compound where these elements are slammed together, no spacing, you can tell me how many of each. Definite ratio. Now, the last part. Usually hard to separate by ordinary means, like filtration or something. If you have water, and you decided you wanted to use that water as a source of hydrogen and a source of oxygen. In other words, you wanted to decompose it, rip it apart, you've got to do something pretty drastic. That you got to zap it with a current of electricity, or you might have to heat it to really, really, really high temperatures, higher than your stove would go, because your stove is just going to have it boil and go out into the gaseous state. So if you want to decompose most substances down to the elements, you got to really zap it with something. So I've got some compounds here that we can take a look at. This white powder, magnesium sulfate, this is the active ingredient. If somebody in your family has really sore, tired feet, you sometimes buy Epsom salts at the pharmacy, and they soak their feet in a solution, a water solution. This is the active ingredient in Epsom salts, magnesium sulfate. Calcium carbonate, chalk. It's finely powdered here, it's been ground up, but chalk, like for the old blackboard type things. Also, some of the tablets people pop for their calcium carbonate. Okay, I believe they also put this stuff in Tums and some of those things because it will act as a base and neutralize some of your stomach acid. But this is what it looks like in pure form. Here's an interesting one. And this is a problem we have here in the South. This is manganese 2 chloride. Now, that should be a pale pink solid. Okay, I didn't heat it up. It did not melt. What happened is some substances have the tendency, they absorb water from the air. Well, here in the south, where it's humid almost every day of the year, this can actually pick up moisture from the air and dissolve itself. And so this one, because I've been using it for quite a while, has picked up enough moisture that it's actually dissolved itself. So let me pass this one around. You can take a look at the compounds that are here. This one is interesting. If you wanted to, this is one you might want to smell, but how would you smell it? Waft it towards you, exactly. Let's see. Yeah, give that a whiff. Does that smell familiar? Mothballs, exactly. Naphthalene. And so, organic substances, substances that have carbon in them, a lot of them have very distinctive odors. So this is naphthalene. Actually, mothballs can be made out of two different things. You all may be too young to know about this, or you live in the wrong part of the country. But I grew up in the Midwest where it gets very cold in the wintertime. We had two entire wardrobes. We had wools and sweaters and things like that for fall and winter. And then for spring and summer, we had cotton and lighter stuff. So we would store one set of clothing half the year. And we had chests that we put it in, and you put in mothballs, compound like this, to be sure insects didn't attack and chew up your sweaters over that 6 months where you didn't have them hanging up in your closet. So naphthalene. Also, I can't imagine this, but if any of you do not like cats, and that's just a bizarre thought, but if you do not like cats, cats do not like naphthalene. And so if neighborhood cats are getting into your flower beds or something, you can sprinkle, supposedly, sprinkle a little of this around in your flower beds, and the cats supposedly won't go near. I mean, they're not going to eat it and die. You're not going to be a cat killer. But they don't like the odor, they'll stay away. Now, I've not tested that because I love cats and I take up strays, and so I don't worry about chasing them away. But if you had potted plants in your home and your cats were using them as a litter box, you could put a little of this, in the dirt, and maybe the cat would use something else. Okay, so we have here, first two, compounds and elements. First two definitions there. Then, atom, the word atom. Historically, the word atom comes from a Greek word, and it means indivisible. In other words, you can't split it apart. Well, in the last century, by the early 1900s, they started realizing, yeah, you can split an atom apart, and there are smaller particles that go to make up the atoms, but they kept the name. And this is how we define atom today. Smallest particle of an element which has the properties of the element. Smallest particle of an element. Now notice one thing. You do not use the word atom when you're talking about compounds. You're only talking about elements. Here's a hypothetical experiment. I have this big block of pure gold. Okay, if I really did, I'd probably retire and live, I don't know, in the Bahamas or somewhere. Okay, I've got this big block of gold. I subdivide it. I take this half, I subdivide it again. I keep subdividing and subdividing. It's hypothetical because the atoms are so small you can't see them and you can't work with them individually, of course, with your hands. But if I could keep subdividing, the last little thing that I would have that would still be identified as gold would be an atom. Now, let me just put an aside here and kind of update that. With nanotechnology now coming out, nano, 10 to the minus 9th meters. Small, small, small. You think this is a meter. Okay, really tiny, tiny particles that they're talking so much now in our pharmaceuticals, putting them on car undercoatings, the nanoparticles, particles down at that size, that what I understand is particles. If you had gold nanoparticles, the properties actually would be slightly different than a big hunk of gold as far as melting point.